Hi everyone, I'm Victor Magri from Lawrence Livermore National Laboratory, and today I'm going to present my work with Peter Lindstrom about a general method for progressive data compression and retrieval. The amount of data generated by scientific experiments has been growing very fast over the last few years. If we look at the Large Hadron Collider experiments, for example, it produces about 1 petabyte of data per second. At the same time, overall memory bandwidth of high-performance computers has been growing slower than compute power, and data movement often becomes a bottleneck in post-processing pipelines of simulation results. In this context, lossy data compression is a solution for reducing the cost of data movement and alleviating this bottleneck. In some applications, though, it is difficult to decide before post-processing how much information can be discarded through lossy compression. For example, let's take a look at climate modeling. A domain scientist might want to study how the temperature in a given area changes, while in another study they might want to look at averages across time. Each of these analyses pose different constraints on how much information can be discarded when compressing simulation results, and usually a conservative lossy compression strategy is taken to meet the most strict analysis requirements, which leaves performance out of the table. In this work, we propose a method based on progressive data compression and retrieval that allows for post-processing compressed data at multiple levels of precision. Our framework is general in the sense that it can be applied to any lossy compressor. It works for any level of precision up to lossless compression. It allows for distributed storage across different media types, and lastly, it is easy to use and implement. Let's take a look at how our method works. The central idea is that we use a sequence of error tolerances to build higher precision approximations of an input data, with the only restriction that tolerances need to be decreasing. In this process, data compression is performed with an arbitrary error-bounded floating point compressor. In the next slides, I will demonstrate how the construction algorithm works. For this purpose, let me introduce some notation. X represents the uncompressed data or ground truth. X tilde I is the approximation at iteration I. Xi is the correction. Ei is the error, and tau I is the error tolerance at iteration I. Finally, C and D are operators representing compression and decompression. We start by compressing and decompressing the original data with the largest tolerance tau1. This builds the first and coarsest approximation x tilde 1. Then we compute the difference between the original data and first approximation, yielding the error field E2. Next, we compress and decompress E2 by using the error tolerance tau2, leading to a second correction field x2. We then sum the correction field with the previous approximation to obtain a new approximation with finer details. Then we subtract the ground truth and recent approximation fields to obtain the new error E3. This process is then repeated as many times as the number of components requested. Condensing the steps just described in a single figure, we get this illustration where x tilde variables denoting approximate fields are shown on top, and the x variables denoting corrections are shown on the bottom. We note that our approach effectively stores the corrections in compressed format, so that the approximations can be reconstructed later. Translating these steps into pseudocode, in the left box we show the algorithm for running the construction phase, while in the right box we show the pseudocode for running the reconstruction phase, where approximations are built. Note that both pseudocodes are short and non-intrusive with respect to the underlying compressor used. In addition, the second algorithm is only a subset of the steps of the first one. Now let's look at numerical results. We tested our framework with 4 well-established lossy data compressors. The first ZFP is based on block transforms as JPEG. Next, SZ is a modular compressor based on Huffman coding. Spur is based on wavelet transforms, and lastly, mGuard is a multi-level compressor. Our framework is flexible in terms of how the error tolerances are chosen. For this study, we define them as a geometric progression with initial term equals to tau1 and ratio equal to 2 to the power of minus delta. Here, delta controls the granularity of our framework, and smaller values lead to more components. For a given target tolerance, use it as stopping criteria for generating new components. In the following slides, we refer to the use of our framework on top of existing compressors as multi-component compressors, and we use the prefix M to denote each of them. Let's start by looking at errors. For generating these and the following results, we use datasets available in the SDR-Bench collection. This plot shows the ratio between measured and target errors as a function of the target errors for the multi-component compressors at delta equal to 4. Error-bounded approximations should lie below the red line y equals to 1. And that is the case for most of the data points in these plots, except in one case that is close to machine precision. Next, we look at compression efficiency through a metric called accuracy gain, which indicates the number of bits inferred by the compressor as a function of aggregate rate. This plot shows results for ZFP and MZFP at true granularities with delta equal to 4, 6, and 8. We see that higher values of delta improve the compression efficiency for MZFP. On the other hand, in general, the MZFP variants show similar but smaller accuracy gains than ZFP at low rates, and the differences increase at medium rates, which can be explained by increasing randomness in components. Finally, at high rates, the accuracy gain for MZFP approach vertical lines as measured errors tends to 0. We also compare the efficiency of multi-component compressors to IDX2 and PMGuard, which are methods that support progressive data compression natively. In general, we can see that accuracy gains of multi-component compressors are similar if not superior to IDX2 and PMGuard. MSPER, light blue curve, is an example of superior efficiency in this case. In addition, the multi-component compressors always show better accuracy gains at high rates. Our approach also supports lossless compression, which is an interesting feature for checkpointing and restarting use cases, for example. The plot in this slide shows lossless compression ratios for various datasets and multi-component compressors. In many cases, the multi-component compressors achieve lossless compression ratios greater than 1, indicating that data is reduced, and they compare reasonably well with ZFPR and FPZIP, which are specialized methods for lossless compression of floating point data. Lastly, we note that the native progressive compressors IDX2 and PMGuard cannot achieve lossless compression. Finally, we show the execution times for performing construction and reconstruction in the right of the multi-component compressors as a function of resulting errors measured in infinity norm. For comparison purposes, we also show results for IDX2 and PMGuard. We can see that MSPER and MMGuard are the slowest methods due to their underlying compressors being slower in this case. On the other hand, MSZ and MZFP are competitive with IDX2 and PMGuard. Particularly, they are always faster in the reconstruction phase and similar, if not superior, in the construction phase. From these results, we can affirm that our approach is competitive in performance with other progressive compressors available in the literature. Lastly, I would like to illustrate a use case of our approach. Let's take a look at an example with varying precision requirements according to the visualization task. In this case, we showed 9 renderings organized in a 3x3 table and generated when doing post-processing of a numerical simulation result. The columns show renderings of the same derivative order applied to an input field with increasing precisions from top to bottom. Rows show renderings generated from an input field with the same precision for increasing derivative orders from left to right. As is well known, differential operators of increasing orders magnify round-off errors. Thus, higher derivative orders are more susceptible to compression artifacts. For this example, when the goal is to analyze results for the zeroth derivative, low-level precision as in the top left corner is enough, while when the goal is to analyze second-degree derivatives, then a higher level of precision as in the bottom right corner is better. Our progressive approach allows for retrieving only the data necessary for a given post-processing task. Now, concluding this presentation, we proposed a general framework for achieving progressive data compression and retrieval of scientific data. Our method is independent of the underlying lossy compressor used to generate components. It is easy to use and incorporate into post-processing pipelines. It shows competitive rate distortion trade-offs and performance when compared to other solutions. And it supports any level of precision up to lossless compression. Our method does have a few limitations though, which I would like to mention. The first is that it requires additional computational time and storage space than standard lossy data compressors. Next, it also requires additional buffer space for generating components during the construction phase, but overall we believe that the benefits outweigh the costs of our approach in many use cases. Lastly, we are looking at developing a general multi-resolution progressive framework as well, with the goal of having a similar method as described in this presentation, but targeting spatial resolution. And we have already been able to generate some interesting results as you can see in this figure. This concludes my presentation and thank you for your attention.